Welcome back to Partial Differential Equations. I'm Dr. Jeff Groh. Today we're going to talk about integral transformations, integral transforms take the form you feed in a function and it outputs a function. You'll be integrating that function against what is called a kernel. You're integrating on the variable t, but the kernel has both t and s, and that allows you to end up with a function of s. There are many kinds of integral transforms. There's the Fourier or Fourier transform. There's the Laplace transform. There's the Legendre transform. There's the Poisson transform, and so on. Many different kinds of integral transforms, each characterized by a different kernel and perhaps different limits of integration. To this point, we've talked about the Fourier series, and we have in particular a Fourier basis. If f is piecewise smooth, and 2L periodic, we have this basis where n goes from 1 to infinity. In this case, f is, in the sense of almost everywhere equal to, which means everywhere except on a set of measure 0, a naught plus the sum as n goes from 1 to infinity. Here we'll have an cosine of n pi x over L plus bn sine n pi x over L. So f has a representation as a sum of these sinusoidal functions plus a constant. Here, the ANs are arrived at by projection and the BNs by projection onto the sines. And a naught, of course, by projection onto the unit 1. This method worked pretty well, but again, provided f was 2L periodic. What if your function is not periodic? But it is defined on the entire real line. Recall that the set of L1 functions are those so that the integral is finite. And our theorem goes like this. If f is piecewise smooth, and L1 on the real line, then our function can be represented, and again, this is in the sense of almost everywhere, But this time, instead of using a sigma, we're going to have a continuous set of coefficients, and we're going to integrate from 0 to infinity. The coefficients are going to be functions, let's say, of omega. We'll integrate out this omega, and how do we get these coefficients in order to represent our function, again, in terms of these sinusoidal functions, but with a continuous varying omega. That period can be stretched out as long or as short as you want. And here's the answer. You guessed it. We'll integrate out our function and we'll integrate out x here. And the b of omegas are defined in a similar way. As before, wherever f has a jump discontinuity, the Fourier transformation representation of f will converge to the average of the left and right limits. The a of omega and b of omega are the Fourier coefficients, and these coefficients are linear transformations on f. In fact, it's easy to see that all of the integral transforms of the sort that we are studying here are linear transformations. T of f is defined to be the integral from a to b of f of x k of s x dx. Then one t of f plus g is t of f plus t of g, and 2 t of a constant times f is a constant times t of f, the two properties of a linear transformation. And this is pretty easy to see. We can prove that in one fell swoop by looking at t of cf plus g. And that's going to be the integral from a to b of cf of x plus g of x times k of sx dx. We can break this up as to c f of x k of sx dx plus the integral from a to b of g, using the first property of linearity of the integral. The second property of linearity of the integral allows us to pull constant factors out of the integral, which gives us c times t of f plus t of g, and that completes the proof. As an example, let's try this on a function. Now the function has to be integrable. So I'm going to make this function 0 as long as the absolute value of x is bigger than or equal to 1, and 1 when the absolute value of x is less than 1. So our function looks like this. The axis goes here, with 0 in between, -1 to 1 here. It's definitely integrable. The integral will be 2. And so it fits the hypotheses with only 2 jump discontinuities. It's only piecewise smooth. So now let's figure out what our coefficients are. We'll have 1 over pi, the integral from -infinity to infinity of our function up against cosine omega x. Now between -1 and 1, f will take the value of 1, 0 everywhere else. That has the effect of just limiting the limits of integration to go between -1 and 1. When we integrate cosine, we'll get this 1 over omega sine omega x, and then we'll have 1 over omega pi. When we evaluate at 1, we'll just get sine of omega, and then we'll subtract. Plugging in -1, the negative will come out. That'll cancel the subtraction, and we'll get 2 over omega pi sine of omega. For b of omega, it's even easier. We'll have 1 over pi integral from -infinity to infinity f of x sine omega x dx. 1 over pi integral from -1 to 1, just as before, sine omega x dx. Now, sine is odd. And when you integrate an odd function from -a to a, you get 0. Now, according to our theorem, we need to reconstruct our function by integrating from 0 to infinity our, in this case, a of omega cosine omega x d omega. Integral from 0 to infinity of twice sine of omega over pi omega times cosine of omega x d omega. Now you might remember that there's a product to sum identity. In case you don't remember it, recall that the sine of a plus b is the sine of a cosine of b plus the sine of b cosine of a, whereas the sine of a minus b is the sine of a cosine of b minus the sine of b cosine of a. And if we add these two, these are going to cancel. We'll have the sine of a plus b plus the sine of a minus b equals twice sine of a cosine of b. And it's exactly this that we're going to use at the present time. I'll factor the pi out, and then we'll have this 1 over omega, and it's going to be the sine of the difference, omega minus omega x, plus the sine of the sum, omega plus omega x, all over this omega d omega. We're going to break this into two integrals. The first one is sine of omega times 1 minus x over omega, and the second one, sine of omega times 1 plus x over omega d omega. Now we'll do a substitution on each of these. We'll substitute back in the end, so we won't bother switching the limits of integration. On the first term, we'll make the following substitution. U is omega times 1 minus x, so that du is 1 minus x d omega. We don't have the 1 minus x, we'll have to divide that over, giving us this substitution. On the second term, u is omega times 1 plus x, and du then is 1 plus x times d omega. We'll divide the 1 plus x over and have this substitution. We'll have then 1 over pi. We'll have integral from dot to dot. I'll not worry about that. We'll have sine of u over, let's see, omega is u divided by 1 minus x here, but d omega is du divided by 1 minus x, and we'll have cancellation. On the second integral, it's also going to be sine of u over 1 plus x, du over 1 plus x, those going away. And now we have the integral basically of sine x over x dx. You might recall from calculus 1 that the integrand sine x over x has no elementary antiderivative. And that would seem to be quite a quandary. However, The simple solution is to define a function that is the antiderivative of whatever sine x over x is. And that's going to be called the sine integral. The sine integral is, because I said so, the integral of sine x over x dx. And so what we get here is 1 over pi of the sine integral of u. But on this term, u was omega times 1 minus x. You see, I'm switching back to the original variable. And on the second term, we'll also have this sine integral, and it's going to be of omega times 1 plus x. And we're evaluating from 0 to infinity. We normalize the sine integral so that sine integral of 0 is 0. You can choose whichever constant integration you want and then adjust it so that you always get 0. After all, we have an odd function divided by an odd function. The integrand is even. When you integrate an even function, you get an odd function. So you expect to get 0 with the constant of integration being 0. And so we end up with 1 over pi times the limit as L goes to infinity of the sine integral of L times 1 minus x plus the sine integral of L times 1 plus x. And to this discussion, we need to add a certain factoid, something that can be proved that we're not going to do right now. If you take the limit as L goes to infinity of the sine integral of L, you get pi over 2. And if you take the limit as L goes to minus infinity of the sine integral of L, you get minus pi over 2. What happens next depends upon what happens if 1 minus x and 1 plus x are both positive. If 1 minus x is greater than 0, that means x is less than 1. If 1 plus x is greater than 0, that means x is greater than negative 1. And if both of those happen, that means x is between negative 1 and 1. So if x is between negative 1 and 1, what happens? 1 minus x and 1 plus x are both positive. The sine integrals will both be going to infinity. You'll end up with pi over 2 on both of those, which adds up to pi. And so multiplying by 1 over pi, you get 1. We're covering the original function here. The question that remains is, what happens when you're on either of the other sides? Well, if x is, let's say, bigger than 1, you get a negative here and a positive here. So if x is bigger than 1, you'll get to pi over 2 from here and negative pi over 2 from here, which gives you 0. And what happens when x is less than negative 1? Well, if x is less than negative 1, you'll get a negative here, but a positive here. So you get pi over 2 here and negative pi over 2 here. So we've recovered everything except what happens at 1 and negative 1. Well, if x is equal to 1, then you get 0 here. If x is equal to 1, this will be 2L. It's like sending L to infinity. You get pi over 2 times 1 over pi. You'll get 1/2. If x is equal to negative 1, you'll get 0 here and a positive thing here. You'll end up with pi over 2 times 1 over pi again. You'll get 1/2 again. So as expected, you get the average of the endpoints of these limits, the one-sided limits, as you approach this step function discontinuities. We have this factoid that we didn't prove, and I want to point out something. If the Fourier integral representation theorem is true, then we can use the last example to prove these two facts. So we'll make these factoids hinge on the proof of the Fourier integral representation theorem. Note, may use the Fourier integral representation theorem to evaluate integrals. As a hasty example, let's consider the function cosine of x for x values between negative pi over 2 and pi over 2 and 0 otherwise. Then let's look at the a of omegas. Those are going to be 1 over pi, integral from minus infinity to infinity. Let's see, we'll have our function at x times the cosine of omega x dx. We'll limit this integral to go between negative pi over 2 and pi over 2. We'll have cosine of x cosine of omega x dx. Both of the factors in the integrand are even functions. And since they're both even, you may as well double this and integrate from 0. It's at this point that we need to use a product to sum identity. You'll remember that cosine A plus B is cosine A cosine B minus sine A sine B. And cosine A minus B is cosine A cosine B plus sine A sine B. And so if we add these two, these will cancel out, and we'll need this too, because these will double up, and we'll just have the sum of those. And so this gives us 1 over pi, the integral from 0 to pi over 2. It's going to be the cosine of omega x plus the cosine of omega x minus x dx. We can rewrite this as x times omega plus 1 and x times omega minus 1. And then the integrand, let's see, we'll get sine of x times omega plus 1 over omega plus 1 plus sine of x times omega minus 1 over omega minus 1, 0 to pi over 2. Of course, when you plug in 0 for x, both of those are 0. So what happens when you plug in pi over 2? Let's see, we'll have the sine of pi over 2 omega plus pi over 2 after we distribute. And we'll have sine of pi over 2 omega minus pi over 2. And so it's just a question of what happens with these translations now. If you translate sine by pi over 2 units to the left, which is what happens when you add pi over 2, you end up with a cosine. So this ends up being cosine of pi over 2 omega. And when you translate sine pi over 2 units to the right, you end up with a minus cosine. So we can factor out the cosine pi over 2 omega. We're left with 1 over omega plus 1 minus 1 over omega minus 1. When you subtract fractions, you do this kind of analysis. Since we're subtracting, the omega minus omega will cancel out. We'll have a negative 1 minus negative 1 that gives us negative 2 cosine pi over 2 omega over pi times, let's see, we have omega squared minus 1, and we can rewrite this as 2 cosine pi over 2 omega over pi 1 minus omega squared. If we look at the other terms, we'll have an even function times an odd function integrated from negative a to a. Those must be 0. So we can recover through the Fourier representation integrals, the Fourier integral representations, by the function f by integrating these up against their basis elements. The original function will be the integral from 0 to infinity. We'll have our 2 over pi coming out, cosine of pi over 2 omega, cosine omega x over 1 minus omega squared d omega. And so this integral, which seems like a very difficult integral to evaluate, is in fact this function. Analogous to truncating a Fourier series is not integrating all the way to infinity. We'll integrate to nu, let's say, instead of all the way to infinity. This gives us a kind of partial sum, if you will. When we truncated Fourier series before, if we had a function with a discontinuity, we always ended up with a Gibbs phenomenon. What happens in this case? Let's go back to our function f of x is 1, provided you're between negative 1 and 0 otherwise. And let's look at the partial sums in this present context. If you run through the analysis, you'll get the integral from 0 to nu of 2 sine of omega cosine of omega x d omega over omega pi. The other term being having coefficients of 0. Because it's sine and cosine, the product to some identity will have this form. We'll still have this omega here. This 2 goes along with the sine times cosine. It's going to be the sine of the difference plus the sine of the sum. And we'll end up with 2 integrals. Let's see. We can factor out the omega on each of these terms and break this into 2 separate integrals. You can see that on the first integral, it's sine of omega 1 minus x over omega plus the sine of omega 1 plus x over omega. Here we'll use u equals omega times 1 minus x, so that du is 1 minus x. The omega will divide by 1 minus x, and keep in mind omega is u over 1 minus x. We get the same kind of cancellation that we had before. We'll end up with a sine integral. So we still have the 1 over pi. It's going to be the sine integral of omega times 1 minus x, and then plus the sine integral of omega times 1 plus x, and we're evaluating from 0 to nu. Sine integral of 0 is 0 again, so you just end up with nu plugged in here and here. as an approximation. So a natural question is, how well does this represent the original function for different values of nu? Let's see if we get the Gibbs phenomenon.
Let's try plotting this function. I'm going to choose nu equals 10. Our approximation g is defined to be x goes to, we had 1 over pi times the sine integral, and in Maple that's a capital S lowercase I, of nu times 1 minus x, close the sine integral, plus the sine integral of nu times 1 plus x. There's our function. We'll plot that between -2 and 2, and you can see that at nu equals 10, truncating the integral that goes to infinity at 10 instead, we don't get very good results. We should get better results by going to, say, 100. And we do. You can see that we get a better approximation to our little digital bump square wave, but we definitely see the Gibbs phenomenon still present with these Fourier integral representations of the original function. Even if we're truncating an infinite integral to a finite integral, we still get these Fourier Gibbs phenomenon. We can get a slightly better graph by using more points to plot the graph. What happens if we go to 1,000 instead? It should be quite a bit better. We still see the Gibbs phenomenon, this overshoot on each of these endpoints. It's something that you can't get away from. It's going to be a feature.
So we see that the Fourier integral transform generalizes the Fourier series that we saw earlier and allows us to describe functions that are not periodic on the real line. There's one further generalization that we need to talk about, and it's the complex form of the Fourier transform. We're going to denote it by f hat. When you put a hat over the function, that means the complex form of the Fourier transform has been applied to that. And it's going to be defined by 1 over root 2 pi for a normalization factor. We're still integrating with respect to a real variable, and it's going to be of the function f of x e to the minus I sx dx, where I is the imaginary unit. We're integrating x out, and so we end up with a function of s. Just by way of notation, we might denote the Fourier transform by a fancy f, thinking of it in terms of a linear transformation, but that's also going to be equivalent to f hat. Also note that f hat of 0 is going to be 1 over the square root of 2 pi, the integral from minus infinity to infinity of f of x. If s is 0, we just get the integral of f of x. Now, we require that this integral be finite, so we're going to assume that f is an element of L1. So these are going to be integrable functions. We also have an inverse Fourier transform that we're going to define a notation for like this. It's going to be 1 over root 2 pi integral from minus infinity to infinity of f of s. We'll have to assume this is some kind of function that has had a Fourier transform applied to it perhaps, or just some function of s, e to the positive I s x ds. There should be some natural questions in your mind. If you do the inverse of the Fourier transform, do you get f? And maybe likewise the other way around. Do these really form inverse transformations? And in the other notation, just this. So let's do a quick example. How about f of x is 1 if the absolute value of x is less than a and 0 otherwise? Let's calculate f hat. Now we'll have our f e to the minus sxi dx. This function is going to be 0 unless x is between negative a and a. And in that interval it's 1. So we'll have e to the minus isx dx. We have then 1 over root 2 pi. The integral e to the minus isx divided by minus is is going to be evaluated from negative a to a. This gives us 1 over root 2 pi. We'll have this minus is. If we multiply by I over I squared is negative 1. That'll cancel the negative here. We'll just have an I here. We'll still have this s. We're going to get e to the negative ias minus e to the positive ias. And so we can apply the Euler identity here. E to I theta is cosine theta plus I sine theta. Due to Euler, we have I over s root 2 pi. We're going to have cosine. Well, cosine of negative, the negative will go away. Plus I sine, the negative will come out. And then we'll subtract cosine of as, and then plus I sine as, and the cosines go away. We'll double up on the sines. We'll have another, well, the negative can come out of what's left over. The I can come out, cancel the I here, making a positive 1. Getting rid of the i's, and we'll just have 2 sine as over root 2 pi s. And we've found the complex form of the Fourier transformation of this function. Now let's see if we can undo it. Before we try this, we should make sure that this function is integrable. You have a sine as, but an s in the denominator. Remember, sine x over x has the following limit. Despite the fact that when you plug 0 in for sine, you get 0. And when you plug 0 in the denominator, you get 0 as well. So you get 0 over 0, which is undefined. But we spend a long time in Calculus 1 proving that you do in fact get 1. And you can obviously use L'Hopital's rule as well. So let's see if we can apply the inverse Fourier transform, complex version of the Fourier transform, to this function and see what we get. I'll express it in this particular instance as fancy f inverse of f hat of s. I suppose we could do it like this as well. Keep adding the different versions of the Fourier transform over the top of the previous ones. And let's see what we get. It's 1 over root 2 pi integral minus infinity to infinity of 2 sine as over s root 2 pi e to the I sx ds. First thing we'll do is move the root 2 pi out, canceling this root. Then we can cancel this 2, so we'll have a 1 over pi out front. We'll have here sine as over s e to the isx ds. I should note before proceeding, f hat of 0, you should put an a here and an a here. That way these will match. The limit as s goes to 0 will give you 1 from this. You'll have 2a over root 2 pi. We'll now apply the Euler identity to e to the isx. We'll have cosine of sx plus I sine of sx ds. Now, keep in mind that sine as over s is an even function because it's odd divided by odd. Cosine is even, so these two multiplied together will be even, but sine is odd. Which means if we integrate this last term, an odd function times an even function, which is odd, from negative a to a, you'll have 0. So we really only need to integrate this function here, but that function we really only need to integrate from 0 to infinity because what's left over is even. We'll apply the product to sum identity now. We'll bring the 2 in here. And we'll have 1 over pi, integral from 0 to infinity. It's going to be the sign of the difference, as minus sx, plus the sign of the sum, as plus sx, still all over s ds. S will factor out. We'll have a minus x here, s times a plus x here. And we'll end up with the sine integral of s times a minus x plus the sine integral of s times a plus x. And keep in mind we're evaluating from 0 to infinity. The sine integral at 0 is 0, so we'll get 0 when we plug in 0 here and here. What happens as we go to infinity? Well, it depends upon where x is. If both a minus x and a plus x are positive, that implies that x is less than a, but also x is greater than negative a. So again, we're between negative a and a. What do we get? As we go to infinity, since these are positive, we'll have pi over 2 plus pi over 2, which is pi times 1 over pi. You'll get 1. What happens when x is bigger than a? If x is bigger than a, you get a negative here, and so you'll have negative pi over 2. You'll get a positive pi over 2 here, so we get 0. And so what happens when x is less than negative a? If x is less than negative a, you'll get a positive out of this. So this will go to pi over 2, but a negative out of this goes to negative pi over 2, and you get 0. Now, strictly speaking, what happens at a and at negative a will be irrelevant, but you can guess that what you'll get is the average, as you should expect. So you can see, by applying the inverse Fourier transform, we were able to recover the original function almost everywhere. The only difference might occur at the endpoints where we have discontinuities, at the jump discontinuities. So far, for one example, the inverse Fourier transform cancels out the Fourier transform. However, this might not happen for all functions. There may be classes of functions for which this equation is false. So we need to know what the hypotheses of the theorem are going to be. Let's look at another example. Let's suppose we have e to the negative x when x is greater than or equal to 0, and 0 when x is less than 0. So the function decays to 0 and is 0 for negative values. This is going to be integrable. It'll trap a finite area if we integrate this. So the complex form of the Fourier transform should apply here. So let's calculate f hat 1 over root 2 pi integral minus infinity to infinity. Well, we may as well knock off everything below 0. Get e to the minus x, e to the minus I sx dx. And so we have 1 over root 2 pi. The integral from 0 to infinity, e to the, we'll combine these, we'll have minus x times 1 plus is dx. 1 over root 2 pi. We'll have e to the minus x 1 plus is of negative 1 plus is evaluated from 0 to infinity. Now, anytime I have e to the negative x times 1 plus I times, who knows, some number b, that's e to the negative x times e to the negative ixb. Euler's formula tells us that the second factor is going to be cosine of xb minus I sine xb. So the pure imaginary part only gives rise to oscillation. The first part gives rise to an exponential decay. And so this will be integrable in the limit as x goes to infinity. You get 0. I'll put this negative out here. When you plug in 0, the top is going to be 1. Negative, negative makes positive. So we're going to have this 1 over root 2 pi. We'll have 1 plus is. To put this into a standard form, it's customary to multiply by the complex conjugate. And when you multiply complex numbers, you don't FOIL, you FLIO. first, last, inner, outer. That combines the terms in an order which gives you the real numbers first and the imaginary numbers second. So we're going to have this 1 minus is root 2 pi, and the rest is going to be, well, when we do the first, it's 1. The second is going to be 1 plus s squared, and then the inner and the outer will cancel out, leaving us with the Fourier transform 1 minus is over the root 2 pi times the quantity 1 plus s squared. We know that Fourier series were wonderful in terms of constructing solutions to partial differential equations. But there's yet another important feature of these complex forms for the Fourier transform, and it has to do with the following theorem. This only applies to functions for which the Fourier transform exists. But first of all, what's the Fourier transform, the complex Fourier transform of a derivative? It's going to be a function of s when you're done. Does this Fourier transform, an integral transform, do something about these derivatives? And the answer is yes. You get is times the Fourier transform of the undifferentiated function. In other words, these complex Fourier transforms eliminate derivatives. This is going to help us solve differential equations, as well as partial differential equations, as we will soon see. A lot of our partial differential equations involve second-order derivatives, so it's only natural to wonder what this does to second-order derivatives. Well, you get two factors of is, which gives you negative s squared, times the Fourier transform of the function f. Obviously, by induction, we'll have the following. If you have the nth order derivative of some function and apply the Fourier transform, you're going to get is to the power of n times the Fourier transform of the function f. We'll assert that 2 and 3 follow by induction from number 1, so it's sufficient to prove number 1. The proof is obviously going to depend upon integration by parts, so it's only going to work for those classes of functions for which the integration by parts will work. So let's do the Fourier transform of f prime. That's 1 over root 2 pi, integral from minus infinity to infinity, of f prime of x e to the minus I sx dx. We want to integrate f prime, not differentiate it. So in our integration by parts formula, we'll use e to the minus isx as u, and dv will be the thing that we integrate, f prime of x dx. So that du is minus is e to the minus isx dx, and v will be f of x. We'll encapsulate this to set this aside. It's always uv minus integral v du, and so we get f of x e to the minus isx from minus infinity to infinity, 1 over root 2 pi times the whole thing, minus f of x times this negative is e to the minus isx dx. Now, if f is integrable, then it has to go to 0 at both endpoints. So this e to the isx part is just oscillatory, bounded between -1 and 1 in terms of modulus. So f itself is going to go to 0 as we send x towards either of these two endpoints. So the first term is going to be 0. And as you can see, all that's left is is times the Fourier transform of the original function. And so that is the end of the proof. What happens in the Fourier transform of x times a function? And the answer is we get I times the derivative of f hat, the Fourier transform of the function. And what happens if we have, this is part 1, part 2, x to the n? Well, we'll have I to the n times the nth derivative of the Fourier transform of the original function. Part 2 follows by induction from part 1. So again, we really only need to prove part 1. You'll note that this is very similar to the theory that we developed in a course in ordinary differential equations for the Laplace transform instead of the Fourier transform. The proofs go very much the same way as well. So I'm going to look at I dds of this Fourier transform of my function. We're integrating from -infinity to infinity. It's going to be f of x e to the minus isx dx. And under suitable smoothness conditions, we can interchange the integral and the derivative. That's interchanging two limit processes, which is not always guaranteed. And so we'll have, under suitable smoothness conditions, the derivative and the integral can be interchanged. These are both limit processes, so interchanging is not always guaranteed, but if we assume suitable smoothness on the function f, we can do this. We'll have the derivative on the inside now. The f of x won't affect anything because it's constant relative to s. The f of x can come out when we take the derivative of e to the negative ISS x with respect to s, we'll get a negative ix. The negative I can come all the way out front. Negative I times positive I is 1. So we get the integral from -infinity to infinity. We'll have an x left over, f of x e to the minus isx dx, and that is the Fourier transform of x times f. And that gives us the end of the proof. You might recall the convolution of two functions from a course on ordinary differential equations. It's denoted by f convolved with g, and for convenience here, which we don't usually do in a course on ordinary differential equations, we're going to put a factor of 1 over the square root of 2 pi out front. It's going to be the integral from -infinity to infinity, f of s minus x g of x dx. This is by definition, so we accept this. The theorem that will be important to us is that the Fourier transform of f convolved with g is the Fourier transform of f times the Fourier transform of g. The proof goes pretty much as you might expect. The Fourier transform has a 1 over root 2 pi, and then it's f convolved with g times e to the minus isx, this is of x, dx. We'll have e to the minus isx. Now the f convolved with g. That's going to be 1 over root 2 pi, the integral from minus infinity to infinity of f of x minus t, g of t dt, and then dx. The trick is to reverse the order of integration. We can bring this function inside of this integral because this integral is with respect to t, and there are no t's here, so it's constant. When we reverse the order of integration, we can bring the function g out, like this. This ends up just being a translated version because we can set x minus t equal to u. du will be dx, and so x will be u plus t. We have 1 over root 2 pi, integral from minus infinity to infinity, 1 over root 2 pi g of t. Let's see what we have here. Integral from minus infinity to infinity. X gets replaced by u plus t. We'll have e to the minus isu times e to the minus ist f of u du dt. This e to the minus ist can come out of this integral, and we're left with the Fourier transform of f. 1 over root 2 pi, integral from minus infinity to infinity. We have e to the minus ist g of t. We're taking the root 2 pi here along with this to give us the f of Fourier transform of f evaluated at s. Let's see, dt. This part depends only on s. And what's left over is the Fourier transform of g. And that's the end of the proof. Let's do a quick example. We've seen this function before. A little digital square wave, 1 between -1 and 1, 0 everywhere else. And we've even seen that the Fourier transform of this is 2 over root 2 pi sine of s over s. My question is, f convolved with f, first off, note that if we do the Fourier transform of f convolved with f, we get this thing squared. Reducing the fraction a bit, we have this. All we have to do to recover f convolved with f is to calculate an inverse Fourier transform. We make the claim that f convolved with f is the square root of 2 over pi times 1 minus the absolute value of x over 2, at least on the domain between negative 2 and 2, and 0 otherwise. We prove this claim by calculating the Fourier transform of this hypothesized f convolved with f. And to this end, we'll write 1 over the square root of 2 pi. Because of the restricted domain, the integral will only go from negative 2 to 2. Square root of 2 over pi, 1 minus absolute value of x over 2, e to the minus isx dx. We cancel the 2's and combine the pi's. I have a 1 over pi out front. Now, we are integrating from negative 2 to 2, 1 minus absolute value of x over 2. Using the Euler formula, we'll have cosine sx minus I sine sx dx. At this point, note that the first factor is an even function of x, and sine is odd. So when you multiply an even function times an odd function, you get an odd function. And since we're integrating from negative a to a, the last term contributes nothing. What remains is even, and since it is even, you might as well integrate from 0 in the lower limit of integration and double the integral. That allows you to get rid of the absolute value. At this point, we use integration by parts. U is going to be 1 minus x over 2. dv is cosine of sx dx, so that du is negative 1/2 dx, and v is the sine of sx divided by s. Putting this aside, we'll have 2 over pi. We'll have uv minus integral v du. We have this negative 1/2 and the s. And all that's left is sine of sx dx. On this first term, when you plug in the 2 in this first factor, you get 0. And when you plug in 0 in the second factor, you get 0. So the first term contributes nothing. And what remains, we'll distribute the 2 over pi and get 1 over pi s. When we integrate sine, we'll have negative cosine of sx divided by s. Let's see, the negative 1 over pi s squared will be out front. We'll have cosine of 2s minus 1. If we distribute the negative, it sure looks like a half-angle identity for sine in what's left over, except we're missing the 2 in the denominator, so we will compensate by dividing by 2 and multiplying by 2. So we now have 2 over pi sine squared of s divided by s squared, and that completes the calculation. An example that's important for the applications is the Gaussian. Which we'll take in a simplified form as e to the minus x squared. This will be important in solving the heat equation. Also note by a simple computation that I always use in my Calculus 2 class. The integral from negative infinity to infinity of e to the minus x squared is the square root of pi. So in our example, I want to do the Fourier transform of e to the minus a x squared over 2. And I want to prove that you get 1 over the square root of a times e to the minus s squared over 2a. Actually, I'll have you do this by Maple or some other computer algebra system as an exercise. Let's look at the Fourier transform of this Gaussian. We have this e to the minus a x squared over 2. We have e to the minus I sx dx. Notice that here we'll have the cosine of sx minus I sine of sx dx. This being an even function, this being odd, and integrating from negative a to a. The second term contributes nothing. By hypothesis, this is 1 over the square root of a, e to the minus s squared over 2a. If s is 1 and a is 2, then what we're getting here is 1 over root 2 pi, integral from minus infinity to infinity, e to the minus a is 2, x squared, cosine of s is 1, it's going to be x, is, if a is 2, we have 1 over root 2, e to the minus, let's see, s is 1, a is 2, 1/4. We can cancel the square root of 2's and move the root pi over and get the integral from minus infinity to infinity of e to the minus x squared cosine of x dx is the square root of pi times e to the negative 1/4. But now we're just playing games. We'll see about Fourier transforms and solving partial differential equations in our next lecture.